So in this part of the tutorial, we'll continue discussing about the R programming. Let me load telecom calls dataset. I will try to import it, and I've placed the files here. So let me choose this dataset, which is telecom calls. There we go. And now let me load this. All right. The moment you look at the data, there should be some alarming aspects that you should be able to see. Right? For example, if you look at this data set, you have the account ID, you have the number of voicemails, total day calls, total local calls, and customer service calls. But one thing that would catch your attention, or that has to catch your attention, is minus 99 and 99 here. And we have a minus 99. How can the number of calls be negative? Number of calls can be 0, that is okay, but number of calls cannot be negative, absolutely. That gives me a further indication that I have to analyze even this 99 here, right? Because everyone at a high level is taking 7 calls, 8 calls, 3 calls, 12 calls, so on and so forth. And I just get a sense that this is an outlier. 99 calls, that's an outlier. Say I've analyzed this and found that wherever you had no data, the no data field was filled manually, or was filled, because of some system problem as 99 and minus 99. So we have to replace these back to NA, right? These are junk values. These are all junk values. You have to change that. So how do we do that is the exercise all about. So you use the function apply. We apply telecom calls margin 2. If you have margin equal to 1, it's going to apply this for rows. Margin is 2 would apply to each and every column. Apply on telecom calls, on each column of telecom calls, this function. Wherever you have x equal to 99, or this pipe delimiter is or, x is minus 99, you replace these values with NA. Otherwise, you let the input value be as is, or you let the data point here, entry, be as is. So that is a function that we have written, if else. So let me run this, and I'm assigning it to another object called clean underscore calls data. There we go. So if I call this now, you see here that wherever we had an NA value, wherever we had 99 and minus 99, that got replaced with NA. Yeah, that's the best part. So you have 1, 2, 3, 4, 5th position, which is minus 99. And the 5th position here is NA. 1, 2, 3, 4. 4th position is 99 here. The 4th position is NA. Right? So on and so forth. So wherever you had 99 and minus 99, that got replaced with NA. All right. Now you can perform a lot of operations on that. Say you're trying to once again apply on this data set, right? Margin equal to 2 is for each column. You're trying to find out the average of all the values, and you're also providing additional attribute which says, or argument which says na.rm equal to true. So you want to calculate the average. At the same time, you also want to exclude the NA values. Right? So let me run this. There we go. So we have the summation, or we have the mean rather, of account ID. We have the mean for number of voicemails. And since we have mentioned that na.remove equal to true, the na values have been discounted from the calculation. Otherwise, the answer would have been NA. Here also the answer would have been NA. Right? Here also the answer would have been NA. If you do not provide that additional argument which is na.remove equal to true. All right. When we use this apply, all you're trying to do is we are applying this particular function which says take the summation of all the columns and na.remove equal to true. How do I know that I need to take summation of all the columns? Because we have mentioned margin equal to 2. If it was 1, it would have calculated the summation for each and every row basically. So let me run this. So we have the summation of account ID, you have the summation of number of emails, so on and so forth. All of a sudden you now can perform a lot of operations on this. Of course, this is all exploratory data analysis. And if you have a large data set, this is a small data set, right? Which has only 10 rows. If you have a large data set, how would you identify the outliers? We identify the outliers using box plot. And we pick up that outlier and try to analyze those outliers and determine on whether those are truly outliers or those are genuine values which have to be retained in your analysis, right? So box plot would tell you or give you an indication about what those outliers are, and you're expected to further analyze these outliers and take a call of deleting these or retaining. All right. And these are a few things that we have discussed early in our tutorial. Now, let us install this package called Lattice. Here we have the Bardley data. If I say view of Bardley, you'd be able to see the data. Bardley, I'm assuming I need not explain about Bardley, right? So beer, etc., you know, is an output of this Bardley. So let me do a question mark of Bardley and let us try to understand this. Bardley is a data set which is available in the Lattice package. That is the reason why we have installed and loaded the Lattice package here. Here we have the total yield in bushels per acre for 10 varieties at 6 sites in each of 2 years. So when you look at this data, you have 2 years of data, 1931 and 1932, right? It's given here. We have in total 120 observations, and we have 4 variables. Yield in bushels per acre, you can think about this as the place where you actually grow, right? And here are the various factors. I believe these are the various, barley main products. Wisconsin number 38, Trebby, so on and so forth. And we have 2 years here, 1931 and 32. And we have 6 levels here. Grand Rapids, Duluth, University Farm. These are the locations where farming is happening basically. Right? And that's the data. You can further explore this data. So that's your Bardley data. Let us proceed further. You can also look at the dimensions. When you look at the dimensions of this data set, you get to see rows by columns. We have 120 rows and 4 columns. And you can also look at the structure of the data, which says there's a data frame. You have yield, which is number. Variety has factors with 10 levels. Year, you have 2 levels, 1931 and 1932. And site is a factor with 6 levels here. You can do an L apply you're trying to find out the unique length of X, right? That's the function that we have written on Barley dataset. So if I run this, you would see a list appearance. L apply, you would see a list kind of a representation. Here is a list kind of a representation. If I do an S apply, it's a better representation over L apply, wherein you'll have yield, variety, year and site one beside another as if it's a table. So here also we have a function which is going to calculate the unique length of the various variables, and you're applying that on Barley dataset. So here we go. So I have 1, 1, 4, 10, so on and so forth. It's neatly arranged basically. And if you try to apply this, if you try to run the function apply, and you're providing 2 here, and you're trying to find out, all you're trying to do here is you're trying to apply this on margin 2. Margin 2 is for columns basically. So for each column, you're trying to come up with number of unique entries, length of unique entries, right? And we have another apply function which is tapply. If I want to calculate the average of yield, and if I want that to be represented based on sites, different sites available, we have 6 sites. So for each of the site, you get to see what is the yield, average yield. Let us run this function. Tapply. There we go. So we have site, which is Grand Rapids, and you have the average yield for that. And by looking at this, it's very clear that Waseca has the highest yield, followed by Crookston, and third highest is Morris, so on and so forth. Yep. Also, you can start expanding this. If I do this, what do you think will happen? You'd get to know average yield for each and every site for both the years, because you have 2 years. For the year 1931 and 1932, you will have all the sites and the average yield which will be published. Let me show you that. There we go. So we want the average yield, and we are trying to represent the data based on years 1931 and 32, and you also have each and every site and the yield corresponding to that. And it's very clear that in the year 1932, Morris has the highest yield, right, or second highest yield. However, in the year 1931, it was Waseca, right, followed by Crookston, so on and so forth. These are the functions which are heavily used for your data exploration. For data exploration activities, this is what you tend to use. All right.